Welcome to This Explainer. Today, we're going to unpack one of the absolute most fundamental rules of the universe. And we're starting with a massive cosmic mystery. You know, we hear about energy all the time, right? We pay energy bills, we eat food for energy, we try to conserve energy. But on a grand universal scale, what are the actual absolute rules governing all this power?
So here's a huge existential question for you. Will we eventually just run out of energy? Scientists have spent literally centuries studying how things move, how they fall, and how they power our world. And to get to the bottom of whether we are slowly draining some finite cosmic battery, we first need to look pretty closely at the different forms this phenomenon takes in our everyday lives.
Section 1. The many faces of energy.
Take radiant energy, for example. It's possessed by oscillating electric and magnetic fields, though you probably just know it as light energy, or maybe electromagnetic radiation. The most vital example of this is the light we get directly from the sun. It actually involves both potential and kinetic energy, and it is the absolute starting point for so many of the complex processes that keep our planet alive.
Then, we've got chemical energy. Literally every single bite of food you eat is packed with potential energy, stored super tightly in its internal molecular bonds. Whether it's a plate of vegetables or a piece of bread, your body is essentially looking to unlock that internal fuel to keep you moving and functioning.
And of course, there's electrical energy. We're talking specifically about current electricity here, which involves both kinetic and potential energy possessed by flowing charges. This is the energy flowing through the walls of your house right now, lighting up our homes and powering our screens. But here's the critical catch. Absolutely none of these energy types exist in pure isolation forever.
Moving right along to Section 2, the Great Energy Shapeshift.
Because here's the thing, energy is essentially a cosmic shapeshifter. It's constantly converting from one form to another. Think about it. A plant transforms radiant sunlight into stored chemical energy, and then an animal eats that plant to power its kinetic movement. Consider a simple electric light bulb. It turns electrical energy into radiant light, but it bleeds off a bunch of thermal energy in the process. Now contrast that with a car's combustion engine. That engine transforms the chemical energy locked inside gasoline into the kinetic energy of a moving car, while also generating immense amounts of thermal and sound energy. And you'll notice a trend here. In almost all of these processes, a significant amount of thermal energy is produced and emitted straight out into the environment.
Which brings us perfectly to Section 3, the ultimate rule, conservation.
Scientists noticed something pretty incredible when they actually sat down and measured these continuous transformations. Let's say a light bulb transforms 100 joules of electrical energy. Well, it might output 5 joules of radiant energy, the light, and 95 joules of thermal energy, the heat. And hey, 5 plus 95 equals exactly 100. The quantity of one form goes down by the exact same amount that the other forms go up. This is the rigid, completely inescapable cosmic accounting system we call the law of conservation of energy. It basically says the total amount of energy that exists right now is all there is and all there ever will be. It literally cannot be created out of nothing, and there is no way for it to disappear. It just changes its outfit.
Let's look at Section 4, the high dive proof.
Evidence of energy conservation is quite literally all around us, but to really appreciate it, you have to look at the visual math. So let's look at a 65-kilogram diver performing a handstand dive off of a 10-meter platform. We're going to track his total mechanical energy, which is just the sum of his gravitational potential energy and his kinetic energy across 3 distinct phases of his fall. We'll start at the very top, then we'll freeze him exactly halfway down, and finally, we'll capture the exact millisecond before he hits the water. Okay, phase 1. Imagine the diver frozen exactly 10 meters up. Because he's perfectly still, his kinetic energy is 0, right? But his gravitational potential energy is fully maxed out. He's got 65 kilograms of mass fighting gravity at a height of 10 meters, so his potential energy calculates out to exactly 6.4 kilojoules. And since his kinetic energy is 0, his total mechanical energy at the very top is just that, 6.4 kilojoules.
Now let's jump to phase 2. He's halfway down. He's lost half of his height, so naturally his potential energy drops right in half to 3.2 kilojoules. But incredibly, his kinetic energy has gained that exact same amount. He is accelerating toward the water, now moving at almost 9.9 meters per second. That gravitational potential energy is literally transforming into kinetic energy as he falls. If you add his remaining 3.2 kilojoules of potential energy to his newly acquired 3.2 kilojoules of kinetic energy, yep, the total mechanical energy is still exactly 6.4 kilojoules.
Finally, phase 3.
right at the water's surface. His height is 0, which means 0 potential energy. But his speed? That is now maxed out at 14 meters per second, giving him a massive 6.4 kilojoules of pure kinetic energy. The transformation is 100% complete. Every ounce of potential energy he held in that initial handstand has been perfectly, seamlessly converted into the kinetic energy of his falling body.
Now here's what is truly fascinating about this whole process. Despite his speed and height wildly fluctuating on the way down, his total mechanical energy never budges from exactly 6.4 kilojoules, not for a single fraction of a second. It didn't matter if he was completely motionless at the top, speeding up in the middle, or moving at maximum velocity right at the bottom. The math completely, undeniably proves the law. The energy was perfectly conserved. It just changed from potential to kinetic.
Wrapping up with Section 5, the final equation.
Let's anchor all of this with a miniature rapid-fire version of our high dive. Think about a 1.1 kilogram camera slipping out of a photographer's hands. As that camera drops 1.4 meters straight down to the ground, we can watch how its 15 joules of initial potential energy seamlessly hands off to 15 joules of kinetic energy right before impact, reaching a speed of 5.2 meters per second. While it's resting in the hands, all 15 joules are potential. Right at impact, the height is 0, so potential energy drops to 0, and all 15 joules have become kinetic. If you look at the math, the total energy never ever budges from 15 joules. It is a beautifully balanced equation every single time.
So, back to our original question. Energy never truly dies, it just takes on a new shape. Whether it's radiant energy from the sun, the chemical energy in your lunch, or the kinetic energy of a fallen camera, you are constantly witnessing the universe's ultimate magic trick. Energy is just passed along, conserved perfectly from one form to the next. So, taking a look around your room right now, what invisible, ancient energy transformations do you think are quietly powering your world in this exact second?